Hello, in this video we're going to introduce linear models and some of the nomenclature around it. And really this is the first video in a playlist that I'm going to call General Linear Models 1. Then I'm also going to have a playlist of GLM2 and GLM3, each probably 40 or 50 videos, and each with varying degrees of different models. But this is the start of GLM1. Now, the definition of a linear model is it's a model that is linear in the parameters. And here's some simple examples. So these two are linear in linear models because the parameters, are all raised to the 1, and they're, it's the sum of them. Now, that doesn't say anything about the x's. They can be of higher degree. Linear models just means the parameters. So here's two models that are not linear. Beta 1 plus beta 1 squared x, where this is a second order term. So it's not a linear model. And then here, of course, that this is not a linear model because it's not written, as the sum of things. So why study linear models? One, it's a simple form. These are simple and they're easy to interpret. They're much easier to fit than nonlinear models. Like this one is a nonlinear model. You have to have optimization programs and algorithms to come up with estimates of these beta parameters. And if we think about it, everything is linear over a certain range. So you can, drill down and get closer and closer to, the graph, and it becomes linear at some point. And so that's another reason. So briefly, we're going to talk about estimation in this video. And the parameter of interest is going to be theta. And our estimator, we're going to call theta hat. And so theta hat is based on a random sample of data points. And now let's talk about some properties of our estimator theta hat. So theta hat is unbiased. Oh, there should be an N in there. Is unbiased for theta if the expected value of theta hat is theta. Okay, that's what unbiased means. The bias of our estimator theta hat is the difference between its expected value and the parameter that it's trying to estimate. This is called bias. The mean square error of our estimator theta hat is the average squared distance from our estimator and our parameter that we're trying to estimate. That's squared, so it's the average squared distance. The mean square error. Now the standard error is actually the square root of the mean square error. The variance of our estimator is this, so it's the expected value of theta hat minus expected value of theta hat squared, and that's the variance. Now note that if theta hat is unbiased for theta, then the variance is equal to the mean square error, right? So if we look at this equation and this equation, what's different is this piece and this piece. And so if theta hat's unbiased, this is equal to theta. So that means the variance is the mean square error. And there's actually a theorem that's called the mean square error is equal to variance plus bias squared. And let's prove that. And one thing about this series is we're going to try to prove everything. Leave nothing, no stone unturned. So the mean square error by definition is this. Now we add 0 to this equation, so we add and subtract the same quantity, which is the expected value of theta hat. Now we're going to expand it, or take the square, but we're going to think of it in terms of this as a term and this as a term, right? So we get this times itself, then this times that, and that times this, so you get 2 of those, and then this squared. And so the expectation is still on the outside. Now let's take the expectation in. The expected value of this is what we were calling the variance of our estimator. And here, this is a constant. When expected value is a constant, this is a constant, this is a constant. So the only thing that's not a constant is theta hat. So when we take this expected value in right here, and so the rest are constants. And then expected value of theta hat minus theta is the bias, and that's squared, so it's bias squared. But look at this term right here, expected value theta hat minus expected value theta hat. That's 0. So this term goes away, and what's left is the variance plus bias squared. And now, as an illustration of these two components, remember that mean square error is the average squared distance. And so, to illustrate this with a picture, pretend like this is a bullseye, and right in the middle is our estimator theta. It's a constant. And so we're throwing darts, or our estimator estimates values here. So it has low variance because they're nice and tight, but it has high bias because it doesn't equal our theta parameter. Here it's high variance and low bias, right? See how spread out they are, so it's high variance, but low bias means on average we're right on this theta. And here is low variance and low bias. And that's kind of a graphical illustration of what's going on here, those two components combined. Now number 6, we're still in the estimation mode. So theta hat is a linear estimator of theta if theta hat can be written as this linear combination of our data. Okay, and this is for some set of coefficients a1 through an. So these are our data points 1 through n, and each one has a coefficient attached to it. Then this is how you define linear estimators. And when we're doing this linear regression and we come up with our estimators for the beta parameters, it's nice to show that our estimates are actually linear estimators of our betas. And so that's what we're doing here. So when we think about optimal unbiased estimators, unbiasedness it's a nice property that says on average we're equal to the parameter that we're trying to estimate. Okay, so if this rectangle represents all estimators of theta, we can have some that are unbiased, so all those are in here. We can have linear estimators. Now some of these linear estimators are unbiased, and some of these unbiased estimators are not linear, and everything out here, is unbiased. I mean biased. It on average doesn't equal our estimator. Okay, so if an estimator within the class of unbiased estimators has the smallest variance of all other estimators, that's called a MVUE, or a minimum variance unbiased estimator, or sometimes called a UMVUE, and uniformly minimum variance unbiased estimator. And that's a nice property, right? We want something that's unbiased and has the smallest variance of any estimator. So the hunt for these UMVUEs is very important because it's a nice property to have in our estimator. Now, an estimator within the class of linear estimators, so linear is nice because they're easy to deal with, easy to interpret, and we want it to be unbiased, so then we're in this area here. So the estimator within the class of linear unbiased estimators having the smallest variance is called a blue, the best linear unbiased estimator. And blues are also also a nice property to have in an estimator. Okay, and we're going to close this video out on listing some important probability distributions that we're going to use throughout this mini series. So the normal distribution, X is normally distributed with some mean, some variance. The standard normal is actually a normal random variable. but it has mean 0 and variance 1. The chi-squared distribution is if we let random variables z1 through zk be independent, identically distributed, standard normal random variables, and then we let w equal the square of each of these added together, summed, then w has a chi-squared with k degrees of freedom. The student's t distribution is if we let z be standard normal and w be a chi-squared with k degrees of freedom, z and w independent, then t, with this ratio, z divided by w divided by k, square root, then this is what we call a t distribution with k degrees of freedom. An f distribution, it's w1 is chi-squared with k1 degrees of freedom, and w2 is chi-squared with k2 degrees of freedom. w1 is independent of w2. And if we let f be this ratio, so it's the ratio of a chi-squared divided by its degrees of freedom, chi-squared divided by its degrees of freedom, w and w2 are independent, then f has an f distribution with k1 numerator degrees of freedom and k2 denominator degrees of freedom. Okay, well, that's all we're going to cover in this video. We're going to kind of keep them short, tight, and concise, but we're going to really cover these general linear models in depth as we go. Now, the next video, we're going to talk about simple linear regression and prove some properties in regards to those. Well, I hope you enjoyed this. This is the start of a journey here. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.